A jet engine can push a 300-ton aircraft to 570 miles an hour, yet its core spins faster than a Formula One engine, spinning around the clock without ever slowing down. A single turbine blade is smaller than your hand, but it survives temperatures hotter than the melting point of the very metal it's made from. Jet fuel and air ignite inside a chamber the size of a trash can, yet that explosion is controlled so precisely it never escapes. And somehow, 10,000 individual parts come together with tolerances thinner than a human hair, inside a machine trusted to carry hundreds of lives at once. A jet engine burns hot enough to melt its own components, spins fast enough to tear itself apart, and endures forces that would destroy almost anything else built by hand. Yet it's expected to do all of this quietly, reliably, and without a second thought from the passengers sitting just a few feet away. That shouldn't be possible. So how do engineers turn raw metal alloys into a machine that survives fire, force, and altitude on every single flight, millions of times a year, without failing? Let's step inside and find out. It starts with the part that shouldn't exist. A turbine blade sits directly inside a fireball hotter than the metal's own melting point, and it doesn't melt. It begins as a nickel-based superalloy, poured molten into a ceramic mold shaped exactly like the finished blade. But this isn't an ordinary casting. Most cast metal cools into millions of tiny, randomly oriented crystal grains, and every boundary between those grains is a place a crack can eventually start. As the mold slowly pulls out of a furnace at a precisely controlled rate, a single seed crystal at the base forces the entire blade to grow as one unbroken crystal, with no grain boundaries at all. Inside that solid metal, laser drills bore hundreds of microscopic air channels, some finer than a strand of hair, so cooling air can flow through the blade's core and escape through pinholes across its surface. That cooling air forms an invisible film hugging the blade's outer skin, meaning the metal itself never actually touches the flame directly. The blade survives fire by never truly feeling it. Every single blade is X-rayed, laser scanned, and weighed to a fraction of a gram before it's trusted anywhere near a real engine. And any blade with even a microscopic flaw is scrapped before it ever spins, no matter how much time and material already went into making it. Even the coating matters. Once a blade passes inspection, it's sprayed with a ceramic thermal barrier, coating only a fraction of a millimeter thick. A heat shield so thin it's almost invisible, yet capable of dropping the surface temperature. The metal actually feels by well over 100 degrees. From molten alloy to a single crystal cooler on the inside, then the fire surrounding it, it's ready to spin at over 10,000 revolutions per minute in the hottest part of the machine. But the blades are only half the story. Behind them is the chamber where the fire actually begins. Inside it, jet fuel and compressed air ignite continuously at nearly 2,000 degrees Celsius, hot enough to melt the walls containing it. Yet the outer casing stays cool enough to touch minutes after landing. It starts as sheets of high-temperature nickel alloy, rolled and welded into a ring-shaped liner that will surround the flame itself. Thousands of tiny holes are precision drilled into that liner, each one angled to bleed in a thin layer of cooler air, forming a protective blanket that keeps the metal hundreds of degrees cooler than the flame just millimeters away. Fuel nozzles atomize jet fuel into a mist finer than fog, mixing it with air in exact ratios so combustion stays stable instead of exploding outward. Igniters fire the mixture only once, at startup, essentially acting like oversized spark plugs. After that first spark, the flame sustains itself continuously for the entire flight, burning roughly 1 liter of fuel every second at full thrust, contained by metal thinner than a coin. Sensors constantly monitor temperature and pressure inside the chamber, feeding data back to the engine's control computer thousands of times a second, ready to adjust fuel flow before anything drifts out of balance. If temperatures ever climb toward the danger zone, the system trims fuel automatically, faster than any human pilot could react, all without the passengers ever noticing a thing. Even the shape of the flame is engineered. Air swirls in through the nozzles at a specific angle, creating a stable, donut-shaped vortex that holds the flame in place at the front of the chamber instead of letting it drift or blow out entirely at high altitude, where the air outside is thin and freezing. Welded, drilled, and pressure tested to withstand forces far beyond what it will ever see in service. The chamber is ready to be bolted into place at the exact center of the engine's fire. The fire needs air to survive, and that air has to be squeezed harder than almost anywhere else on the aircraft. Air entering a jet engine is thin, cool, and low pressure. Seconds later, it's compressed to over 40 times atmospheric pressure and heated by hundreds of degrees without a single flame involved. The compressor starts as dozens of titanium and steel discs, each one machined to hold a ring of small airfoil-shaped blades around its edge, closer in shape to tiny airplane wings than fan blades. Each disc is carved on a 5-axis mill, accurate to a few thousandths of an inch. Then individual blades are locked into precision-cut dovetail grooves so tight they can only be seated one exact way. Stacked one after another, alternating spinning discs with stationary rings called stators, the compressor forms a narrowing tunnel, each stage squeezing the air into a smaller space than the one before it. Every rotating stage speeds the air up. Every stationary stage slows it back down and redirects it, converting that velocity into pressure instead. By the final stage, air that entered as an ordinary breath of atmosphere is dense enough and hot enough to support combustion entirely on its own, having been squeezed into roughly 1/25th of its original volume in under a second. Before it's cleared for use, the entire assembly is balanced to hundredths of a gram and spun at full operating speed on a dedicated test rig, because even a tiny imbalance at those speeds could tear the shaft apart. Some of the earliest compressor stages are made from titanium for its strength-to-weight ratio, while the hottest rearmost stages switch to nickel alloys able to handle the extra heat generated by all that compression, meaning a single compressor can actually be built from several different metals working together. Clearances between the spinning blade tips and the surrounding casing are kept to fractions of a millimeter, close enough that even minor thermal expansion during a flight has to be accounted for in the original design. The compressor is ready to feed the fire, waiting just behind it. 3 separate marvels: blade, chamber, compressor, and none of them mean anything until they're forced to work as one. Assembly happens on a spotless, climate-controlled floor where the compressor, combustion chamber, and turbine, each built in a completely separate part of the factory, finally meet for the first time. Technicians mount the compressor and turbine onto a single central shaft, aligning them so precisely that even a fraction of a millimeter of imbalance gets caught before assembly continues. The combustion chamber slots between them, along with fuel lines, wiring harnesses, and an outer casing engineered to contain any failure internally, rather than let it escape outward toward the aircraft. Once fully built, the engine is wheeled into a reinforced test cell and run for hours, climbing from idle all the way to maximum thrust, while sensors record thousands of data points every second. At some point, engineers fire an entire dead bird, sometimes several at once, directly into the spinning fan at full operating speed, on camera, on purpose, just to prove the engine can survive a real-world strike and either keep running or shut down safely. 10,000 parts, aligned to tolerances tighter than a fingernail's thickness, all have to hold together at once, or the whole assembly shakes itself apart under full power. Engineers also deliberately push the engine past its rated limits during testing, running it hotter and harder than it will ever legally be allowed to fly, just to find the true breaking point before a customer ever does. Only after it survives every single test does the engine get crated, shipped, and finally bolted beneath the wing of an aircraft, ready to do, thousands of times over, exactly what it already proved it could survive on the test floor. That's how raw metal alloy becomes a single crystal turbine blade, a controlled fire, a squeezed column of air, and finally one finished engine, precision, heat, and force balanced against each other thousands of times a minute on every single flight. Every part fighting to destroy itself, held together by tolerances measured in fractions of a millimeter, working in total silence somewhere above the clouds. 35,000 feet over an ocean most passengers never even glance out the window to see. Most of us will never see any of it happen, until now.